Imagine, if you will, floating in the silent, velvet blackness of deep space. A giant, glowing, ethereal clock materializes in front of you, its hands crafted from starlight. Could physics make time travel possible? Today we explore the science, the paradoxes, and the mysteries of time itself. The gateway tempts us with the fantasy of stepping off our designated path in the river of time. It speaks to our deepest desires, to correct our mistakes, to reunite with lost loved ones, to witness history. Is this all just fantasy? Once the realm of storytellers and dreamers, this question now lives in laboratories and on chalkboards. We will voyage from the strange effects of moving near light speed to the crushing gravity at a black hole's edge. Come with me, let's explore the science. We must first understand what we seek to control. The paradoxes, the profound mysteries of time. Time travel sits at the edge of science and imagination, and tonight we test the border. For most of human history we thought of time as an absolute, but Einstein revealed that time is a dimension, woven into the very fabric of the universe. For most of human history we thought of time as an absolute, a universal drumbeat, steady and unchanging, marching forward for everyone. But a young patent clerk imagined something different. Einstein showed us that time is not separate, it is a dimension, inseparable from space. To pinpoint any event you need 4 coordinates, 3 in space and 1 in time. Length, width, height, and when. Imagine a vast flat rubber sheet stretched taut. This is space-time. Place a bowling ball. The sheet curves and dips under its weight. We call this curvature gravity. Mass and energy bend space-time, and that bending changes the flow of time. A clock placed near a massive object will tick more slowly than one far away. Time is a river that can be diverted. Each tick echoes with the birth and death of stars. We follow in the footsteps of giants who questioned the absolute clock. Next, the strange effects of moving at incredible speeds. In short, time is part of the universe's structure, flexible, dynamic, and influenced by mass and energy. Einstein's revelations didn't stop with gravity. Einstein's theory of special relativity unveiled another astonishing secret. The faster you move through space, the slower you move through time. The universe imposes a strict speed limit, the speed of light. We have a set of identical twins, both 20 years old. One twin stays on Earth, the other boards a rocket traveling at 0.999 c. For the traveler, the journey might feel like a couple of years. But upon returning, decades, perhaps centuries, could have passed on Earth. The astronaut, still young, may find family long gone. This isn't fiction. It's a direct consequence of Einstein's equations. For the high-speed traveler, time literally ticks more slowly. The cosmos forces you to trade speed through time for speed through space. All you need is a vehicle that can approach the cosmic speed limit, a technological feat beyond us today, but allowed by physics. So while we don't have a machine that can pick any year at will, special relativity gives a guaranteed recipe for forward time travel. As you approach light speed, the universe around you fast forwards, stars age, civilizations rise and fall, all while you experience only a fraction of that time. The future is out there, waiting for anyone who can travel fast enough to reach it. Speed isn't the only way to bend time. Gravity can stretch it beyond imagination. Speed isn't the only thing that can manipulate time. Gravity can too. Einstein's general relativity tells us strong gravity slows the passage of time. A black hole forms when a massive star collapses into an extraordinarily deep gravitational well. As you near the event horizon, the point of no return, time stretches dramatically. If you send a pulse every second, an outside partner sees those pulses arrive further apart. Seconds stretch into minutes, then hours, then years. For the astronaut falling in, time feels normal as they cross into the unknown. In that sense, a black hole behaves like a natural time machine, at least to the future. If you could orbit a supermassive black hole without being torn apart, and then return, thousands or millions of years may have passed for humanity. Even here on Earth, gravitational time dilation is real, infinitesimal but measurable. It's a constant reminder that time is sculpted by gravity. To travel backward in time, we need more than speed. We need a tunnel through space-time. Enter the wormhole, an Einstein-Rosen bridge connecting distant points in space-time. But can they be traversable? Imagine space-time as a sheet of paper. To go from A to B, you normally cross the surface. Fold it, bring the points together, poke a hole. That hole is a tunnel through space-time, a wormhole. A traversable wormhole could let you step from your living room to a marketplace orbiting Proxima Centauri in moments. If one end is accelerated to near light speed and returned, the entrance could be 2025 while the exit emerges in 1925. By stepping through, you travel through time itself. There's a very big catch. Wormholes want to pinch off into singularities the instant they form. Keeping one open seems to require exotic matter, negative energy, density acting like an anti-gravitational scaffold. We have no idea if such matter exists, but the theory keeps the dream alive. Combine wormholes with time dilation and you get theoretical time machines, entrances separated by years. Even if exotic matter exists, engineering a stable, traversable wormhole is far beyond us. Yet the theoretical possibility keeps physicists exploring the math. To step into the past opens a Pandora's box of paradoxes and contradictions. Next, the paradoxes that make physicists wary of the past. The possibility of traveling to the past opens a Pandora's box of logical contradictions, paradoxes. These puzzles challenge cause and effect. Consider the grandfather paradox. Suppose you build a time machine, travel back, and prevent your grandparents from meeting. If your parent is never born, then you are never born, so how could you have traveled back? Some propose the Novikov self-consistency principle. You might visit the past, but you cannot change it. Perhaps improbable accidents conspire to prevent paradoxes. Now the bootstrap paradox. Give Shakespeare a book of his future plays. Who wrote them originally? The information appears to have no origin. Trapped in a causal loop. One solution, the multiverse. Change the past, and you sprout a new parallel timeline. Your original world remains. You become a visitor in a new reality. That preserves causality, but at the cost of an infinite number of parallel realities. Paradoxes challenge our fundamental idea that effects follow causes. While time travel to the past wrestles with paradoxes, time dilation into the future is measured and real. While journeys to the past remain speculative, the principle of time travel, time dilation, is real and measurable. The most visible example is GPS, a system that depends on precise time. Satellites move fast and sit in weaker gravity fields than us on Earth. Special relativity slows them by about 7 US day, general relativity speeds them by plus 45 US day, net plus 38 US day. Without correction, GPS location errors would grow by kilometers each day. Engineers calibrate satellite clocks to account for relativistic effects. Practical time travel in action. Your phone's navigation relies on Einstein. Everyday time travel enabling daily commutes. Astronauts on the ISS orbit fast enough that they age slightly slower than people on Earth. After 6 months, they may be about 0.007 seconds younger. A tiny leap into the future. We live in a world where time moves at different rates for different observers, and we have the receipts. It's not a dramatic leap, but it is a journey through time nonetheless. Ground teams constantly correct satellite timing to keep systems accurate. Without relativity, navigation would quickly break down. If the future can be measured and reached, should we use it? And should we change the past if we ever can? Time travel touches our hopes and regrets. The human question is as important as the physical one. As we teeter between what is proven and what is dream, we must ask questions beyond math. Philosophy and ethics join physics at the threshold. The temptation to correct regrets or prevent tragedies would be immense, but the consequences are unknowable. Your one act could ripple into catastrophe. Who gets the right to decide which past to change or which future is allowed? If you could see the future, would it strip you of free will, or imprison you with dread? A bright future might breed complacency. Knowledge can be a burden. The greatest danger may be our fallibility. We might cause harm even with good intentions. The past made us. Unravel it and you may unravel everything we know. The power to travel through time could save lives or destroy them. It is the power to play God. Before we pursue the how, we must consider the why and the what if. The decision to change history is not merely technical, it is moral. We have traveled from the heart of an atom to the edge of a black hole. Time is not rigid, it is dynamic, bent by gravity and slowed by speed. The past is guarded by paradoxes and the need for exotic matter. The future, reachable by physics, is already knocking. The quest is valuable. It pushes the limits of knowledge and imagination. Whether or not the past can be visited, studying time reveals the structure of reality. If you had one dial pointing to yesterday and the other to tomorrow, which way would you turn it? Travel to the future is proven. Travel to the past is theoretical. Time remains one of our greatest mysteries. The science is fascinating, the paradox is mind-bending, but our hopes and questions give the quest its soul. Explore the impossible with science.